volunteered me to give something about talking about a hot topic. And when he asked me to identify a hot topic, I figured nothing is hotter than alter magnets at the moment, at least if you go to like the APS meeting or the joint MMM Intermag, there was lots of stuff going on there. Okay, so now that you know what alter magnets is, I'll tell you a little bit, if you're not familiar with it, how to think about it. I mean, we're all familiar with ferromagnetic materials. I mean, that's what we're talking about a lot. And so if you have a ferromagnetic metal, we know what happened. Whoa, wrong button. We know what happens. We get like a splitting of the D bands, and that gives rise to a net spin polarization, right? We have these two bands for spin up and spin down that shifted with respect to each other. And if you look at the Fermi surface, essentially you get an isotropic spin polarization in ferromagnets. And it makes it very useful for magnetoresistance, memory, all this kind of stuff. Now, on the other hand, if you have an antiferromagnet, you have as much spin up and spin down, so naively you expect that there shouldn't be any spin polarization. And in fact, you can be more concise about it. There was this guy, Kramers, who figured out there shouldn't be a spin polarization. Especially, it doesn't really matter what type of antiferromagnet you're looking at here, but as long as the atomic sites for the two sublattices are identical, there should be no spin polarization, like chromium, for example, maybe. But in an alter magnet, the situation is slightly different in that the local structural environment around the two sublattices is different. It has a different crystalline orientation. For example, in this material, potassium ruthenium oxide, you have these octahedra that are rotated 90 degrees with respect to each other. And so it's easy kind of to think about that the electrons associated with this sublattice move differently in this direction versus that direction, and that for electrons that are sitting on this sublattice, this situation is 90-degree rotated. And so indeed what you end up then with is a spin splitting of your electronic band structure that's different in two different spatial directions. So, and if you now average over all directions, you still have no net spin polarization, but you have now a momentum-dependent spin polarization of the electronic band structure. And so that allows you to get all kind of transport properties, anomalous Hall effects, among others. And it's kind of curious, if you look at this, this is probably the paper that everybody reads who's interested in alter magnets, because they discuss it very well. Like one of the examples that I come up with is manganese fluoride, which, heck, that's what Sergio Resende worked on like 5 decades ago. And indeed, it has a spin polarized band structure. Now, for transport, it really doesn't matter because it's an insulator. All the spin polarization are at states where we really don't care. So now I should say this idea of getting spin polarization in antiferromagnets can be much more general. As we said, in a conventional antiferromagnet, we don't expect anything, and this is kind of related that you have both a combination of time and parity together is a symmetry of the material, and therefore this Kramers degeneracy has to hold. But you can do things like Kant, the antiferromagnet. You can do this by applying a magnetic field. You can have a Jarzynski-Maria interaction, so it becomes like a weak ferromagnet kind of material. In that case, you can have a spin polarization very much like in a ferromagnet because you have a net magnetic moment. We just talked about this collinear alter magnets, where you have this because there's different local symmetry around the two sublattices. But you can also have like non-collinear antiferromagnets, and you see if you go through time and parity reversal, you don't end up with the same thing. And lo and behold, you get also a momentum-dependent spin polarization of the electronic band structure there. So these kind of things can be actually fairly common, and this is maybe more the exception of the rule. Whether that really, why this has a different name from this, I don't know. I'm not even sure. So Now, we talked about electronic band structure, spin polarization of electronic band structure. Why should we even care here, right? I mean, we're talking about magnons all the time. So I can come up with like 3 reasons why we may want to care. One is maybe you can get large spin orbitals from the spin polarization. Yes, by all means, have interruptions. This is supposed to be a discussion.
Here, so like very naive question, and more like towards the semantic aspect of the word altermagnets. Is this like a different like phase, ferromagnetic phase? So you know, like how do the authors like argue about this being a specific case of anti-ferromagnetics or being like a completely different phase?
You know, the authors of this paper, they would argue it's completely different, but it's also because they wrote a paper with 3 authors, you know, so they have something specific in mind, what this is hopefully going to give rise to, but some big award. But I'm not sure. I mean, I really think of it as a subclass of antiferromagnets. To my mind, they think it's completely different just by virtue of the difference of the electronic band structure being significantly different. I will show a little bit later that there are other people who think hard about how to classify magnetic materials, and there are even different ways of doing it. But yeah.
Thank you.
Cool. Yes. Sure. Cool. I like it. A lively discussion already.
Is this altermagnet is related to that compensation point where you have spin and moment, and sometimes you can cancel the spin out because of the 2 sublattices, but you still have a finite moment? And
no, so you're thinking of like ferry magnets where you can have sublattices that are really super distinguished by each other because it's like 2 different oxidation states of the same element or 2 different elements all together, and then you can compensate the spin but not the orbital moment or things of that nature. No, this has nothing to do with that. It does, the big distinction is this fact that the local chemical structure of the 2 sublattices is not identical. And so if you look at this example, manganese fluoride, for one sublattices, the neighboring fluorine atoms are along the 110 direction. For the other sublattice, it's along the 1 bar 0 direction. So it's that structural distinguishability essentially that allows to get the net spin polarization then.
it's like, yeah, thank you. That clarifies a lot. So it's basically a canted situation where you have spins oriented in different ways for different sublattices, right?
Well, you have 2 sublattices in this case, you know, where they are pointing in opposite directions, but the immediate chemical environment is not the same. So you can tell the 2 sites apart from each other, just crystallographic already.
But you know what I'm getting at, right? Is to trying to raise up some asymmetric coupling between the different sublattices, because that will fit very well on the talk right here.
Yeah, no. So I mean, so the coupling is the same, I think. And so in this case, like anisotropies and things are also the same. That is not necessarily needed. At least that's what I understand.
So to see if we understand this, there is only one polarization direction in position space, like in an antiferromagnetic. So up, down with respect to some direction in the material. It's not canted through the material, the quantization axis.
That is right. So in this case, the magnetization is completely compensated, and there's a strong C-axis anisotropy, especially like in the cousin of this, if you like at iron fluoride, this anisotropy is really large, for example. But yeah, so that's how collinear altermagnets work. Now these non-collinear systems are different. In my mind, they are also like altermagnets. Other people have different opinions. But
Yeah. Mm.
oh, hey. Yes.
I think that the comedian video misled us to believe that there was some kind of rotation of the magnetic moment in real space, right?
Well,
That's what you were actually
but
commenting on as well.
yeah, so
Yeah.
he's not a physics expert, so don't take his words too literally. But I mean, the atoms around the sublattice are rotated. Here they are, for this sublattice, they're pointing in this direction. For this sublattice, they point in a 90-degree rotated. So in that sense, he got it right. You know, so immediately the
atoms.
chemical environment is rotated.
But the orientation of the local magnetic moments is fixed.
Yeah, so there's a fixed axis, right? So the same here for this material, I don't know. I think the spin direction is probably along the z-axis here, pointing at us. But in the AB plane, you have these rotated octahedra.
Yeah, but then what's the difference between just a collinear antiferromagnet?
So if you take nickel oxide, for example, or cobalt oxide, which is just a collinear antiferromagnet, there the immediate chemical environment around the two sublattices is exactly identical. And so in those cases, so cobalt oxide and nickel oxide will have spin degenerate bands for sure.
Okay.
That's the difference.
I think you can also think about it in terms of the symmetry of the system, right? For an antiferromagnet, you have time reversal symmetry, basically. And for an altermagnet, you don't really have it. But you do have the symmetry where you do both time reversal and a 90-degree rotation. So basically, that's how I usually think about the rotation in altermagnets.
Yeah. I'll point later to a paper that discusses this in all gory detail, and you only like it if you like a lot of group theory. So for me, I like to look at this, okay, the atoms around the sublattices, are they oriented differently? If they are, it's an altermagnet. If they don't, it's an antiferromagnet, yeah. All right. Why should we care? So as I said, one might be large spin orbitox. You have spin polarized band structures, so by passing currents through these materials, you can generate spin accumulations. These spin accumulations may be passed on to the magnetic layer where you want to excite magnons or something. So
Yes, I'm not sure whether you wanted to discuss later, but I mean, obviously we should also care because of the band structures, electron band structures, right? And all this kind of things related to excitons and everything, so...
Sure. Now, this is a conference on quantum magnonics. So in that sense, I thought most of the people here are interested in magnons.
Okay.
But as your excitons connect to magnons, sure. No, I mean, as if your magnon properties are changed by the electronic band structure, of course, yeah. Then you should care. But in most cases, we don't think about it that way. Yeah. Okay, so I thought I'd bring just up one example. This is where they do like spin torque ferromagnetic resonance. So they pass a current through ruthenium oxide, which ruthenium oxide is like the bad boy of altermagnetism. Most papers are written on ruthenium oxide, but there is a big discussion on whether ruthenium oxide is even magnetically ordered. So take all the papers on ruthenium oxide with a grain of salt. It's possible that by using epitaxial strain, you turn it into an antiferromagnet, but the bulk material itself presumably is not magnetically ordered.
So do you know the band structure of this material?
Do I know the structure?
Yeah, the band structure.
The band structure. You look at this paper earlier from Libo Smykal, I'm sure the band structure is in there, under the assumption that it's an antiferromagnetically ordered system.
I'm just trying to think of what is the distinction, a very mundane sort of approach to look at the band structure and see. We know that ferromagnets have spin split bands at the Fermi level. Antiferromagnetism, not quite. And this new materials, this outer magnet, as you showed, it has some spin split bands, but overall, there's no magnetization, right?
That's
so,
right.
Do you think it would be correct to say that, yeah, those materials then, they're different from the ordinary antiferromagnets because they have spin split bands, even though they don't have an add magnetization. At least the ones you showed are like that, right?
Yeah. I mean, so that is certainly a viewpoint, and that's the viewpoint of the proponents of altermagnets being totally different.
But they all sort of break time reverse symmetry. But as Evan said, there are some other symmetries that combined are there, right? I'm not very strong in group theory to say anything else, but I guess.
Okay, so antiferromagnets on their own break time reversal symmetry, but typically under parity symmetry, then if you do put the two together, that's conserved. And then you have to have spin degenerate bands. Altermagnets, this is not the case. And so in this material, again, you have these oxygen octahedra around the magnetic atom that are rotated by 90 degrees. And that's why they have this altermagnetic band structure. And so what they did is they made samples with different orientations of ruthenium oxide, and indeed they see that they get large spin torques indicative of like large spin accumulations in the ruthenium oxide for one orientation and negligible small ones for the other one. And so they suggest that is directly related to this altermagnetic band structure where you have spin splitting in one direction but not in the other. Now, who knows? As I said, it's not even clear this material is magnetic in the first place. Maybe you have spin-dependent states for other reasons. It's purely coincidental. The spin torques that they get are not particularly large. They are as large as platinum, but not much bigger. And I don't know if there's a reason that they would have to be much bigger. So, could be interesting. It's a little bit cumbersome because if you want to use it for sure, you have to have epitaxial, single crystalline samples, and you have to apply the current in a very specific direction. So from a practical point of view, using altermagnets for spin orbit torques or what is probably not the most useful thing. But maybe some of them are really large, I don't know. But anybody has any other thoughts using altermagnets for like spin orbit torques?
Just more like a question regarding like the band structure of magnons. So because here we were talking about like the electronic band structure.
Yes.
So what?
We come to that
okay,
next.
So I'm gonna wait for the band structure.
Okay. So because very well observed. For the magnons, you also expect that the same symmetry consideration may give rise to interesting properties of the magnon dispersions. Namely, in a ferromagnet, we know we have only magnetic moments, magnetic magnons where the chirality of the precession of the magnetization is only one way. It's always only right-handed around the magnetic field, right? Now, in an antiferromagnet, as we can go back to this really super nice tutorial from Sergey, you have two modes. Either one of the sublattices dominates or the other one. And that means either the magnetization precesses one way or it precesses the other way around. So you have two chiralities, but these are degenerate. Now, in altermagnets, it's now possible that if you go in two different directions, that the dispersion will now split for these two different chirality magnons. That actually sounds interesting. Maybe that could be useful. You want to ask your question now, or should I go on?
I can ask one question now.
You can ask any question, as many as you want.
So I was thinking about the last part of your talk, when you're like talking about coupling the Higgs sphere to like microwave resonator.
Okay.
So we know that that wouldn't work super well if we have like an antiferromagnet, just because of like the absence of fringe fields. But like here, since they're not like exactly degenerate, so I think that would be like some net fringe field coming for a fixed Magnon energy with like not the Kittel mode. We have to get away from the gamma point. Gamma point, everything is degenerate. So my question is, would like for instance an altermagnet with Magnon mode that's not the Kittel mode coupled to like a qubit of a microwave resonator?
So I mean, the first thing I would say is, if you have an antiferromagnet, with the dynamics, you do have a net magnetic moment, so you, depending on what the dynamics is. But like in this case, you have a canting of the magnetization automatically, which generates a small magnetic moment that can couple to an external field. So what you were saying earlier is not completely correct. An antiferromagnet does couple to external magnetic fields there too. Now, the main reason why we don't do this, let's say with qubits or so, is because of this canting of the antiferromagnetic moments, the magnetization dynamics, the frequencies of antiferromagnets are much higher. They're typically, like in a terahertz regime, right? And so they are in frequencies that if you do like superconducting qubits, you really don't access easily.
Got it. So just to make sure I understood you, you're saying that if we have antiferromagnetic sphere, so the uniform mode, it's going to be coupled to like a qubit if you, of course, have the same frequency.
In principle, yes.
Okay.
So in principle, yes. But
and can you just repeat the argument again? Because because you have
So when you have this magnetization precession, one of the moments precesses around the effective field the way how it likes to precess. The other moment precesses opposite to the forces that are acting on it, right? And so what this means is that the precession cone angle for one of the moments is always larger than for the other one. Because, I mean, the effective fields given by the crystalline anisotropies are opposite for the two moments. So what that means is the moments always cant with respect to each other, which involves this strong exchange interaction. That's why the frequency is so high. And this also means that you have a net magnetic moment from the canting that you can couple to. Now, these two moments will have opposite chiralities of the motion of these magnetic moments. So if you go back to Rare's measurements where you had the circular polarized microwave fields, if you have a circular polarized microwave field, you couple only to one and not the other. But in an altermagnet, these two modes are also different in terms of energy once you're away from the gamma point.
Thank you very much.
Right, cool. Cool. I don't even have to say that much.
All right. So just to make sure, we do have antiferromagnets which which are in the gigahertz range, right? So we have, of course, we have synthetic. Synthetic, you can do whatever you want. Synthetic means you just make, what are the correct terms? The heterostructure.
Like magnonic crystals?
No, you can use interlayer exchange coupling, for example.
Yeah, so and you can make it in a way that there would be one layer this way, one layer this way. And then there are also natural antiferromagnets, which are layered, like chromium sulfur bromide, or which another one, chromium phosphorus sulfide. And they do have frequencies in gigahertz range. So in principle, you can couple it to a qubit, but to be honest, I don't see in any respect how it would be better than YIG, but maybe there are some aspects which I don't see.
Yeah, and so, I mean, very good point. In fact, we have used superconducting resonators to couple to some of those materials where those antiferromagnetic resonances are very low lying. But yeah, typically this in van der Waals materials where each layer is ferromagnetic and the coupling across the van der Waals layers is very weak. And then the frequencies drop down accordingly. You know? Yes?
Before I ask, yes, don't take my word seriously because I know nothing about antiferromagnetic. What I'm saying is just asking questions, trying to understand it. But then my question is, there is this spin flop for higher magnetic field in a normal antiferromagnet.
Sure.
In the outer magnet, would I expect that this transition would happen in a higher field? Or
No,
particularly?
so in terms of those kind of things like spin flop and the Magnon dispersion to first order, it's not any different. Because, I mean, the magnetic interactions are necessarily very different just because they have this altermagnetic crystal structure.
But then because there is this splitting, I was considering the possibility of having two transitions maybe? I don't know. I'm just
So, no. Well, could the spin flop transition look different in altermagnets? Maybe. I don't know. I mean, so what you do in a spin flop transition is you apply a field along this direction, and so then you also start splitting the two modes because there is a net magnetic moment associated along the longitudinal axis. And so then what happens at the spin flop transition is one of the modes goes soft, and that's when the spins flip. You know? Would this be different in an altermagnetic band structure? I don't think so, because the non-uniform magnetization modes, the energies are higher, so I think they would go soft later than the zone center mode. That would be my guess, but.
Thank you. I think everyone realizes why is a hot topic, right? So every time that I'm looking for that figure, for instance, probably maybe because of Sergio, I'll think about let's say spin-Seebeck effect, because in spin-Seebeck it's one way that you can use to prove the chirality of those modes, because for example in antiferromagnet spin-Seebeck effect, they exist because you create an opening between the two modes, and above the spin flop you see this change in sign. I don't know if someone is following, could be too much specific, but if I look in the outer magnet, should be there.
Yeah.
Already.
So, yeah. So you're absolutely right. I mean, it could be that the spin-Seebeck effect looks very different if the heat goes one direction or 90 degrees differently, right? So there could be definitely interesting situations there.
Maybe just a quickly one. I'm not so sure, but I have the feeling that that thing that the automagnets was there, we just know about it, is because the optical properties of those are, I mean, or what's the issue or the consequences of these things in the optics properties point of view? Because, I mean, for example, if you talk about the egg, there is some correlation between.
Well, so there could be some circular dichroism associated with this, I suppose, right? Just like you can get an anomalous Hall signal in altermagnets. So you can get also a Moog signature from this, right? So that's kind of what's interesting about these altermagnets, that many of the experimental signatures that you associate with ferromagnets are now available for also interrogating the antiferromagnetic structure. I mean, the bigger problem is, in order to see any of it, you have to have a single domain altermagnet also, because if you have two opposite domains, then things will cancel out again. So if you have a magnetic domain that goes from here to there, then the splitting also switches, right? Okay, Yaroslav, ooh. All right, it's like the two sides.
Right, just wanted to mention that we actually worked on spin Seebeck in altermagnet, and it's different.
Okay. So, when I looked at this, I thought, holy shit. And so one of the prime examples of this is manganese difluoride. It's like the antiferromagnet that has been studied to death. Clearly, people must have seen this. I must disappoint you. It turns out people looked very careful recently because of this, and they don't see any splitting of the modes here. So it turns out it's not just the crystal structure alone. There has to be some anisotropy of the exchange interactions also that come into play. So this is a very interesting article, actually, saying the absence of chiral magnons in, but yes.
To answer my question, actually. So probably I should wait.
Okay, sure. But anyway, I mean, so theoretically, if you go back to this PRX paper from Smykal, Zinova, and Thomas, his last name. Yeah, exactly. Jungblut. Whatever. They calculated there should be this Magnon splitting for manganese difluoride. So that's kind of what this is about. And with quite certainty, they've seen this is not the case, at least in manganese difluoride. Not all is lost, though. Here's another material, manganese tellurium. Now, this is a little bit more complicated because it's not just cubic. The symmetries are slightly different. Here, if you look careful enough, you do see this splitting of these two Magnon modes, which theoretically they should have different chiralities. From the inelastic neutron data, they can't tell the chirality of the neutron modes, but they see that there are two. So it's possible you have it in some materials, not in all. The details of the exchange interactions do matter, I think, there. That's all I wanted to say about chiral magnons. And you still have questions about chiral magnons?
So because you have just started touching the point that I wanted to the question that I wanted to ask, but you said that, okay, anisotropy in the exchange parameter. But what about if you introduce anisotropy in other parameters? Because of this chemical structure, there could be other types of anisotropy, like even in the hopping parameter. Could it account for the band split between the Magnon's bands?
Well, it's certainly the anisotropy of the electron hopping that gives rise to the spin polarized electronic band structure in the first place. But for the magnetic one, I think that alone is not sufficient. There have to be some other things that come into play. There's some nice discussion in this paper, which goes probably way beyond what I can recall at the moment. But yeah.
Okay.
Any other questions, concerns?
One quick question related
Sure.
to the previous slide. So they do not see the splitting, and they're claiming that it's due to like missing anisotropy, the previous one. Yeah.
Yeah. Yeah.
Right. But like the theoretical, so my question is, does the theoretical calculation include an anisotropy? Or
Oh yeah. There's a strong anisotropy. The anisotropy manganese fluoride. See, manganese fluoride really is one of the materials where the magnetic properties have been known in great detail. So the nearest neighbor exchange interaction, the next nearest neighbor exchange interaction, those are things that have been measured 50 years ago. The anisotropy is really well known. You can get this for spin flop transition and things. So the magnetic parameters are super well known. I don't recall which one of the interactions. I think maybe these two have to be slightly different in order to generate this alter-magnetic Magnon band structure. And I guess it turns out, and you could imagine that this is the case, right? Because between these two, there are fluorines in between. Between these two, they are not. But I guess there's not a sufficient amount of difference in the anisotropy between these two. My guess is because really the exchange, instead of going from here to there, goes from here to there to here to there to there, right? And so then this one does something very similar. And I think that's probably ultimately why it's not so different.
right. And just like a follow-up question, we know that depending on the frequency you are, reloading light scattering might have like some problems with resolution. So my question is there altermagnets in like more lower frequencies where you could like resolve things a little bit like better?
Well, this is not Brillouin light scattering. This is inelastic neutron scattering. And so with BLS, you wouldn't see this in the first place because these frequencies are all like terahertz frequency. Well, I don't know. Maybe you could. Well, so yes, if you have materials where the coupling is very weak, like these van der Waals type antiferromagnets, then it could be. Now, in these van der Waals type antiferromagnets, what it would require is that each van der Waals layer is like rotated with respect to the next one. Like if they are 90 degrees rotated. There are actually some nice papers that discuss synthetic approaches for making altermagnets. Looking at those, I think it's like a theorist pipe dream. I don't see how anybody could possibly do this. I mean, you could do this maybe with this, where you exfoliate, you rotate, and put it back together or something. That could maybe work, but.
Thank you.
So, just
all right. As I said, the theorist pipe dream maybe. Yeah, computer is patient.
So are you aware of any, what are the, did people try to come up with the minimum model that has the correct ingredients, the minimum, the necessary ingredient to predict something without the complications of all this lattice different, a simplest outer magnet, like how they type, models that would predict something simple that we could understand. Is there such a thing?
Absolutely. I mean, so as I said, there's like a theory paper. There's one nice one from Rembert Duin, but there are others where they essentially just take one ferromagnetic layer which has anisotropic transport and then have a 90-degree rotated layer that's antiferromagnetically coupled, but has now the anisotropic transport in the different direction. And sure, you get all the kind of things that we see here. And if you now also assume that the exchange interactions are anisotropic in these layers, you do get these chirality split Magnon band structures also. That, I think, would be the simplest model for sure. So the ingredients that go in there are pretty straightforward, I think. That's what makes it kind of appealing.
So this exchange in isotropy is important.
For this chirality splitting of the Magnon bands, I think so. That's my understanding, at least. Well, not in manganese difluoride, which is the poster child of anti-alto magnets, apparently. But for manganese tellurium, yes. So there are materials where you do see it, presumably. But yeah.
Yeah, so maybe I'm just not getting something, but like, okay, so having this anisotropy, having anisotropy in the hopping in the electron basis is important for getting this splitting of the spin bands. But if you do some sort of account for super exchange or whatever, and you do J squared over U type, like, you know, going to the insulating limit.
Yeah.
Because MnF2 is insulator, right?
Yes.
So the anisotropy in the spin bands does not necessarily translate to anisotropy in the exchange once you go to the large interaction limit. Is that sort of the way? So I don't know, like just trying to understand.
I think so. I mean, I haven't gone back to looking at why the theorists thought that manganese difluoride would have a chirality split Magnon band structure, whether they really calculated the anisotropy of the coupling from first principles, for example, and stuck that in. Or if they just assumed it's got to be different and then you get something. You know? If it's the latter, well then it's a trivial mistake maybe, you know, or a bad assumption. Okay, cool. This is way livelier than I anticipated.
That's great.
I
guess you have some more?
I have just a few more, especially for the theorists among you.
Okay, so just we are now officially during the coffee break.
Okay, I'll have like 3 minutes maybe.
Okay, good.
So, as I said, there was this discussion, how do you identify an alto magnet in the first place? There are people that look much more careful at the symmetries that play a role here. And so what you can do is, beyond just going, looking at the magnetic dipoles, you can look at magnetic multipole moments, for example. And so Nicola Spalding and her colleague saw, for example, for manganese difluoride, that the magnetic octopole moment with these moments is actually ferroically ordered, and that's part of the reason why it acts like an alto magnet. There are these guys, Roland Winkler and Uli Sülicke, who really went like full group theory and analyzed this in great details, what kind of different multipoles you can have, and they identified essentially 10 classes of symmetries of electromagnetic materials. They call this the standard model of electromagnetic materials. It's a tomb, this article, but if you like group theory, yeah, well, you'll be excited. It's very thorough. I've heard Roland giving a talk about it. I think he's onto something. Much more careful than maybe these original easy ideas about alto magnets. And so alto magnets do fall into some subcategories of all this. One thing that I was interesting, Nicola Spalding pointed this out, that because of this alto magnetic crystal structure, you also expect piezomagnetism. Kind of makes sense. You know, you have like a different chemical environment around one sublattice versus the other. So if you push in one of these directions, you affect one of the spins differently than the other. And so it turns out there's both what is called piezomagnetism and there's anti-piezomagnetism, where the moment of both sublattices grows when you squeeze it. But manganese fluoride is very well known to be piezomagnetic. So this all checks out. So what these alto magnets have for sure is a strong coupling of their magnetic order with the crystal lattice. And so this even gets some Brazilians excited, like Rafael Fernandes, you know, who is now in Urbana. But this he did while he was still in Minnesota. So you can get like hybridized modes between phonons and magnons, and they call it the dynamic paramagnon polarones in altermagnets. Some fancy names, but I mean this looks like what we've been discussing all week so far. So it's not very different. And that's all I wanted to say. And if you have any additional thoughts, let me know.
So thank you, Axel. That was a great discussion. Thanks for putting it together. So Dennis has one more question, quick question, and then we wrap it up.
One very quick one.
So I'll ask you another question. You need to send me a title. So tomorrow we have a session like that, run by Dennis and Christina, so you have a chance to get back.
So in the spirit of the Quantum Magnonics conference, so
Yes.
one of the most important aspect is like coherence of magnons, or the magnetic excitations,
Yeah.
and etc. So have people measured the lifetime of magnons in alter magnets, and if so, what is the Gilbert damping? Are they like good? Are they coherent? Can they be useful in a similar manner as like YIG magnons?
Well, in principle, yes. So like manganese difluoride, again, it's like the antiferromagnet we know everything about. The lifetimes have been measured super carefully, even as a function of momentum. If you go back to this tutorial thing from Sergio, he has that in there actually, and he shows how excellent it actually agrees with theory and what. So, yeah, I mean the damping can be low for similar reasons. It can be why it's low in ferromagnetic systems. If it's an insulator, that helps. You don't have electronic excitations that muddle things up. You want to have ideally magnetic moments that are just spin moments, no orbital moments. So if you have iron 3+, you're already good. That's why YIG is so good, for example. Now, crystalline anisotropies are probably not good. So manganese fluoride, I don't remember what the damping is. It's probably okay, but not outrageously good. But I mean, there's no particular reason why antiferromagnets should be better or worse than ferromagnets in that respect, I think. And for that purpose, altermagnets are antiferromagnets also. I mean.
So thank you very much again, and let's break away for our coffee break.
Cool.
So we should be back at 4:10 maybe.